Continuing our idea of analysis of variance with one factor. So here I have 7 GPAs for business students within 4 distinct programs in the business program. Finance, human resources, and marketing. So I want to know if one of these programs or more of these programs are substantially different in difficulty from the others. Do students in one of these have a clearly higher average GPA or lower average GPA? So, doing an analysis of variance, what is my null hypothesis? All of this data is at the top of page 421 and available here in our exercises on the Canvas page. We'll come back to the data in a minute. I'm going to use Excel for this, but I need to know where to start. What is my null hypothesis? Mike? Right. And so we could write them however we want. The mean for accounting is the same as the mean for finance, is the same as the mean for HR, is the same as the mean for marketing. And then my alternate hypothesis is at least one difference. Okay. If I were going to do this by hand, I'd need 2 pieces of information. I need the alpha, which was given to me in the problem, but I'd also need the degrees of freedom. I need the degrees of freedom for the groups, and I need the degrees of freedom for the entries. So, degrees of freedom 1 is for the groups. What's the degrees of freedom in that case? Four groups, so there's 3. Degrees of freedom 2 is for the entries. Now, normally I'd say, well, it's n minus 1, but I need to take into account the groups here. There are 7 in each, and I take away 1 for each group rather than just 1. If I were going to use the table, I'd now turn to the F table where alpha is 0.05, and I could look up the right F values to figure out what my critical numbers. I need an F left and an F right for my critical behavior. I'm going to do this entire thing in Excel. So I go to my Excel sheet where I have all of this data. It's already stacked out in tables for me, each major being in a column. So I'm going to say, oh, I want to do the data analysis. So I go to data over here on the right. Where's my data analysis page? There we go. Thing was over the size of the monitor. So there we go. Data analysis. ANOVA 1 factor. Right there. Okay. Where's my data? My data is here. Yes, there are labels in the first row, and yes, we are grouped in columns. Alpha is already set to 0.05. Again, that's almost always my default, but they did tell me to use that in the problem. So I want all of this result on a new worksheet. Here it is. And now I should be able to answer this in two different ways. Tell me, how do I know whether to accept or reject my null hypothesis? Those three numbers. Now, I find it interesting here. I've got one p-value. I'm only comparing that to the 0.05, 0.03 smaller. I'm outside the reasonable behavior that this happened randomly. But I also have only one critical F value. When we did the F value for the variance test last chapter, in the homework you just gave me, it said there was an F left and an F right. We were doing all equal versus not equal. We should have two Fs, a lower and an upper. So why aren't we getting two Fs? Why are we only getting one? What most behavior and almost every statistics work does is it turns a two-tail test into a right-tail test. It says, I'm really only worried about this tail. Because if my thing is too low, I just switch which one I call 1 and 2. So I'm actually going to do two F characteristics. Remember that our F calculated value was variance squared over variance squared. But it was which one was which one, group 1 and group 2. It didn't matter, did it? So if I reverse the fraction, that gives me the other F value. So what our Excel calculation does is it takes whichever of those two F's is larger. And it says, look at that one. And then it only compares the right side as opposed to the left and the right. If I didn't have both options built in here, if I had two different F critical, I would have an F left critical and an F right critical. Remember that one is F left is the one out of the table. We reverse the order of the degrees of freedom and then take one over. So I don't actually have to do that because it was done all here for me. Remember, we're looking for our rejection range. P-value is probably a lot easier in this case, in general. Okay, what does that mean? I rejected my null hypothesis. What does that tell me? This is why we write down the hypotheses, so we know what we're actually testing. What's this result tell me? Right? At least one mean is different from the others. So now we can go upstairs to the summary box up here, and we say, oh, let's take a look at what's going on up here. And we say, oh, yeah, there is a clear difference between these majors. And not only that, look at the variances for each major. So here, the accounting major has an average GPA of 2.83, but the variance is 0.255. That's a fairly large variance compared to the others that are 0.03, 0.09, 0.06. So that's got a lot of spread to it. And that variation, along with the lower average GPA, tells me, hey, accounting is a harder major than the other three in this group in a statistically significant way. And then you can say, wait a minute, 283, 302, 324, 337. Marketing is that much easier? It's a full half a grade easier than accounting? That's what this set of information tells me. Now, this didn't come from our school. I don't know where they got this data from, but that's a question I could ask about the programs here or anywhere realistically, right? Hey, which major in the School of Business, which is going to get me the business degree I want, which major is going to be the one that doesn't have me tearing my hair out any further than it already is gone, right? Now, I would have to do a little more analysis if I really wanted to sit down and say, all right, which one is different and by how much? How far out of line? How much does this variance account for the difference as opposed to just the treatment being in each different major? There are several different tests that we can do. There's something called a Tukey test, T-U-K-E-Y. There's a Levin test. Most of these are beyond the scope of what I do most of the time. So I'm going to leave those for now. If you're interested, they require a little more programming behind them. We can't actually do them in Excel. Questions? Okay. So what happens if there's more than one thing that matters? What if I have two factors? Hmm. Gonna matter how many observations I have for each combination of factors. So we said each combination of factors was a treatment. So I'm going to have to look at whether I have one measurement per treatment or multiple measurements per treatment. If I only have one measurement per treatment, then we say this is an ANOVA without replication. So I've got the same idea. I've got my Y value. And then I've got two different kinds of categories. I've got my rows, which I'm just going to call A1 through AR. And then I've got my columns, B1 through BC. And each of these has a value. There's a Y value for A1 and B1. There's a Y value for A1 and B2, all the way up to a Y value for A1 and column C. Similarly, all the way through. So each row and column combination has a single entry in it. One measurement per treatment. Well, now I can start looking at averages. But my averages now come in both row averages. If I go across this row, everything has the same first number. So I'm going to get Y1 dot bar. The dot means that I ignored, I'm averaging over the columns. Similarly, if I go this way, I'm going to get Y2 bar dot. All the way down here to YR bar. If I go down the columns, all of these, I'm going to get Y dot 1 and Y dot 2, all the way down to Y dot C bars. If I average everything, there'll be a global grand average. So I have row means where the dot is in the second subscript. I have column means where the dot's in the first subscript. I understand this is not the prettiest setup, but to me, it's this blue section that's important. All of the Y bar stuff is going to get calculated automatically when we do the actual analysis in the software. So I don't have to do that part. I don't have to do that part by hand. But what's our goal here? Our goal here is to determine if any one of the treatments in the A column over there matters. If any one of the treatments in the B column row up top matters. Do any of these have an effect on the Y value in that spot? Really, I can think of this like a straight line again. Is the value that comes out of Y our grand average plus some result of being in that row, plus some result of being in that column, plus some little random error. But this is the row effect. And this is the column effect. This is the random error. So really, my analysis of variance is still a straight line model, only it's a really more complicated linear equation. You'll notice nothing here is raised to any power or multiplied together in any weird fashion. It's, hey, here's my overall averaging effect. The question is, does this treatment matter? Does this treatment matter? I don't know what's going on. How do we shut it up? Good, you got it. Thank you. Sorry. And I can't control the random error. Random error is going to happen. I'll allow for that perturbation. But if I can somehow say, oh, no, there's a clear variation based on what row we're in, there's a clear variation based on what column we're in, then I'll be able to say, those treatments matter. I'm going to compute a bunch of test statistics again. It's an unpleasant, long calculation. So I'm not going to do it directly. But I am going to say what I'm testing is the same idea. I'm testing the same idea. What's my null hypothesis? There were two different ways we wrote it last time. The way you already mentioned this morning and another way. What's my null hypothesis? If I could connote inside. Something about the T's, the treatments themselves, that I mentioned on Friday, is part of our null hypothesis. Right, but in this case, I've got A's and B's. I've got two different kinds of treatments, right? So my null hypothesis is going to be that all of those are zero. Well, in this case, it will be AJ and BK. They're separate. So I really have two sets of null hypotheses. I have that the rows don't cause any influence. I have that the columns don't cause any influence. So there are actually two distinct null hypotheses, one for each factor. So which row we're in causes no difference, right? So this is the set of hypotheses we get for factor A. What about factor B? The only thing that's different is I change those A's to B. Everything else stays the same. The idea is that, okay, my null hypothesis for the other factor is that all the column cause the same effect. There's no difference being in any column. Notice that isn't quite exactly the same as saying they're all zero, right? I'm saying they all cause the same effect. So really, my ANOVA comes in two behaviors. If both of my null hypotheses turn out to be true, then the only effect is the randomized effect. Whatever our grand mean is, plus the effect from just being in a row or a column, it doesn't depend on the factor. I'm hoping that's the case. Now we have to keep these together. So we might be able to say, hey, being in a row does cause something, but being in a column doesn't. Or being in a column causes something, being a row doesn't. Now, this looks kind of weird to start with, but let me give you a problem to hang our ideas on. I'm going to say the example on page 429 talks about fertilizers and soil type. I have 3 different types of soil and 4 different types of fertilizer. Does which fertilizer I use matter? Does which soil type I use it on matter? I'm going to plant a small section of crop in each of the different soil types, and I'm going to plant 1 for each different type of fertilizer. So I'll have 12 different sections of my fields growing, and I'll be able to say, oh, hey, no matter which fertilizer I use, this kind of soil makes a difference. That would just be one of the effects mattering, the other one not. So I'll be able to make 2 distinct accept or reject behaviors here. I'll be able to accept or reject each null hypothesis independently of the other. So when we set up this big table of information here, we get all of our means and all of our different behaviors. We'll be able to say, okay, based on which fertilizer I'm working with, which soil type I'm working with, I'll be able to see some sort of output. It may be that we really only want to test one of these 2 factors. We really only care about one thing and the other one is just a control. Like in that case, maybe I'm only looking for which fertilizer matters and I don't care about which soil it's in. But I'll use the differences in the soil just to see if that one is always better or that one is always different. That's called a randomized block model. Now that's an interesting phrase. What's a confounding influence? I promise we'll come back to that. We will use that more often. But a confounding influence is something that affects our factor that is known. I did a statistical research paper with one of the students on the volleyball team. And it was very interesting. We did a gross oversimplification. We did a huge number of comparisons in variables. And we found, hey, you know that kill percentages match up with number of kills perfectly? Of course they do. Kill percentages is the number, the percent of kills you did. Kill shots is the number you did, just turned it into a percent. It makes no frickin' difference at all, does it? Whether it's percentage or not. Of course, that's the same piece of data seen 2 different ways. They're going to affect each other perfectly. So my goal is to remove that sort of additional influence. Now, in that case, we almost always put our treatments in the columns. And then we call the row effects the blocks. And then I can randomly assign subjects in each block to a treatment. Okay, all of the things in the sandy type of soil, I'll put fertilizer 1, 2, 3, 4. But over here in the wet soil, I'll put 4, 2, 3, 1. It doesn't matter where they go in each block, just that I keep the treatments in order. But in that case, I'm really only looking for the column effects. I'm not looking for the row effects. Okay, again, there's a giant pile of mathy bits on page 430 and 431. But it comes down to figuring out the square error for each of the factors and then that random error. The A piece, the B piece, and that epsilon. And if I can figure this out, I'm going to do two different F values. I get an F value for the A and I'll get an F value for the B. Row F value and a column F value. Page 433, problem number 21. Concerned about Friday absenteeism, management examined absenteeism rate for the last three Fridays in 4 different plants. Does this sample provide sufficient evidence to conclude there is a significant difference in treatment means? Okay, wait a minute. What? What is this problem asking? I'm going to need 2 sets of hypotheses. It's asking me if absenteeism on a Friday afternoon is different based on what plant I'm at or which Friday it was. That's my 2 sets of factors here. So in terms of the rows, what's my null hypothesis here? The A null hypothesis would be for the rows.
Absenteeism on all Fridays.
So it doesn't really matter what Friday it was, average absenteeism on any given Friday is the same. Then the alternate hypothesis is at least one of the Fridays is different. How about the column null hypothesis? There's no particular difference between which plant you're at as to how many people are absent. So I don't know where these plants are, but it might be, Jeanette and Delmont and Pittsburgh and Latrobe all have the same absenteeism. Yes or no? Alternate hypothesis then, at least one plant has different absenteeism. More people skip out on a Friday in Greensburg, or more people skip out on a Friday. Less people skip out on a Friday in Delmont, I don't know. But that's what my analysis will now tell me. It'll tell me, oh, either which Friday it is matters, or which plant you're at matters, or both. These choices are independent from one another. So again, I go to my data pile and I say data analysis, ANOVA single factor. My data, E3, no, it's not there anymore. My data is here. Grouped by columns, labels in the first. Oh, wait a second, that's not right, because I shouldn't be doing a single factor. I should be doing two factors. Notice they give me the option with or without replication. We're doing replication here. There's only one data value per treatment. That's without replication. Input range. Click. Actually, I want to include the labels. I'll tell it I included the labels. And now it should be able to tell me at a 5% confidence what's going on. Oop. Oh, we'll do that. I can't include that extra top line where the word factors where I need to only include the row immediately outside the numbers. All right, wait a minute. Here's all my information. For the rows and for the columns, it gave me a critical value F, it gave me a p-value. It gave me a calculated value for F. You tell me, do the rows matter? There's my row information. Row was Fridays or plants. Look back at the data. Was rows Fridays or plants? So, does which Friday it is matter? Critical value is 5.14. My calculated value is 8.61. Am I in the reject or accept section? We're in the outside little shaded area. In the F test, my F critical is smaller than my F calculated, I should reject. My p-value was 0.017. My alpha was 0.05. It's very rare that this happens just by chance. So which Friday it is matters. Some Friday must have had more absenteeism than another. As a matter of fact, now if I go up and I look at the average, I can say, hey, the 11th absenteeism was 25, but on the 4th it was 21, on the 18th it was 22. All right, the 11th was out of line with the other ones, wasn't it? How about which plant? Plants were the columns. The column matter. And my p-value is 0.0002. Compared to 0.05, that's a lot smaller. I'm way further out there in that shaded region. It's really important which plant I'm at. And then I go back and I look at the averages here. 20.3, 18, 29, 25. Yeah, that third plant has substantially more average absenteeism than the first two. The fourth one's in the middle, so I would say, yeah, there's some variation here based on where you are. Which one matters more? Column or row? Because so from a practical perspective as the boss, I can go in and I can say, hey, you guys are absent on Friday more often than not, than other plants. But I can even say from a statistical perspective, which one has a larger effect. The one with a larger effect is the one with the larger F value. The one with the larger effect is the one with the smaller P value. It's much less likely that that column effect happened by random chance than the row effect. 0.0002 versus 0.017. It's literally 10 times smaller. 0.02 versus if I round, 0.02 versus 0.002. Yeah, that's a much smaller. 100 times smaller. That's a really big difference. Both have a significant impact on absenteeism. Which plant I'm at and which Friday is. So I don't know what was going on the 11th that made it much more of a Friday to be absent than the 18th. Because usually like St. Patrick's Day is the 17th, right? I wouldn't expect the 11th. Maybe there was a football game in town. Who knows? Whatever it is, that's the answer. The row effect does matter. The column effect matters. The column effect matters more in this case. I could go a step further and I could plot this data. I could plot this data two different ways. If I go back to this data, I could plot this, insert line chart. There it is by date. 4th, 11th, 18th. 4th is blue, the 11th is red, the 18th is green, and it's pretty clear that the red line is always higher than the other two at every one of these points. So regardless of which plant I'm at, absenteeism was higher on the 11th. That's a nice clear connection, isn't it? I could also plot this the other way around. Select data, switch row and column. See that option right there? That'll make me plot by plant instead of by date. And again, I can clearly see, oh yeah, the third column, plant number 3 is at the top no matter what day it is. Plant number 4 is under that no matter what day it is. 1 and 2 are the lowest by a clear, distinct margin. So which plant I'm at is definitely a factor. This data might actually be more easily distributed among my employees. I could go, okay, hey, look, plant managers, look, which plant I'm at matters. Whoever's in charge of number 3, you guys are out on Friday more often. I don't care what they're pre-gaming for, tell them to stop doing it. Make sense? Mostly. Please notice the two important pieces. I'm not doing this by hand. The hand level calculations for this are just arduous. It's not worth it. I did this in a minute by clicking on the data set here. But more important than that is, after the fact, I analyze the information and say, this is what my conclusion is. Now, we saw in this that there was another type of ANOVA. Even when it was two-factor, there was the replication idea. So what happens if I have more than one data value per treatment? What if I don't have the same number of data values per treatment? How can I account for all of this? That's what we'll do next time. But next time is not Wednesday. Next time is Friday. Wednesday is the test for chapters 8, 9, and 10. Remember, you are allowed a new formula sheet. You are also allowed to bring the formula sheets you used previously. You'll have to turn them all in. I will turn them all back to you. Same as the previous ones. Formulas, definitions, statements of theorems, no worked out examples, no samples. Other than that, bring your stuff. I will give you the tables as well. You are welcome to use the programs in your calculator. I just want explanations written down on the exam page. I will see you all then. You should also have a homework for me if I didn't already get it from you.